Now, equilibrium then is the last two of the five assessment criteria for this particular learning outcome. So it's still learning outcome 2, all right? It's rates and equilibria. And the problem here is that you meet this constant, which also has the letter K as a symbol. And yeah, it can confuse matters, which is why I do the rates bit first and give you the assignment on that, and then almost do this as a standalone piece. But like I say, I don't want to get too far with it on this session, because there's no point in trying to launch into the calculations this side of Easter and then have essentially sort of 3 weeks or so before we come back to it, because you know you'll have forgotten it. So I'm only really going to do the very basic sort of foundations of this, and hopefully get on to, I've got a demonstration that goes with this, which I hope I've got in the right place. So, and then yes, we'll sort of put it on hold until after Easter. Okay. Now, the idea of equilibrium relies on you understanding the idea that reactions are usually reversible, and they are often described as examples of dynamic equilibrium, which means that you've got constant change going on. And it's not something you necessarily experience in everyday life, but if you think of something like you've got a cup of tea and you stir some sugar into it, and you put 1 spoonful in and stir it and it dissolves, you put another one in, it dissolves. How far do you go, you know, before it stops dissolving? I don't know, but let's say 6 spoonfuls, you get some left at the bottom. So has it stopped dissolving? It hasn't, actually. What you've got there is an equilibrium where some of the sugar is solid and some is in solution, but you still have some going into solution and some coming out of solution. And it's like we met with osmosis, where you'd got that, you know, what we would consider an end point, where we had the isotonic point for the potato. It wasn't that osmosis stopped, was it? It was just that it was equal in both directions. So that was an equilibrium. And this idea of equilibrium in chemistry is quite important, particularly for industrial applications, because if you've got some expensive reactants to make a useful product, then you want your equilibrium to use up all your reactants and make as much product as you like. You want your equilibrium to be near the product end of the reaction. And you can tinker with quantities of substances, you can change temperatures, pressures, all sorts of things to actually change where an equilibrium position comes. But I need to explain what we mean by equilibrium first, and this is where we start to use the two-way arrow. You're not going to need to type it, I realise, in any assignments, but if you do need to use the two-way arrow, the code for it is on the notice board over there. So what we're looking at is this idea of reversible reactions. Help if I spelt it right. And what we're looking at then is not just reactants, stop using capital letters, not reactants just with a one-way arrow becoming products, but we have the option of it going that way or that way. And you might have one or more on either side. So it's that use of the two-way arrow is really important in representing an equilibrium. Now, I'm going to use examples that I think I originally got off Chem Guide. So, you know, if you want additional information on this, then that's fine. You know, it will be there. It will be the same information. I just find it sort of helps to be sort of referring to one source. If you put together in a closed container, and this is often what we have to specify, if we're looking at reactions between gases, they will be in containers of a known volume. All right, and if we take hydrogen and iodine, then they will react together to form a gas called hydrogen iodide. All right, so we can use a one-way arrow and high at the end. All right, so hydrogen and iodine will react and you'll get hydrogen iodide. But the situation here is that if you've got this in a closed container, I should put in here, shouldn't I really, hydrogen and iodine gases in closed vessel, I'll say, rather than container, because that sounds like you could just put them in a box. But this would be a, like perhaps a glass flask with a bung. So if we've got hydrogen and iodine gases in a closed vessel, they will react together if those are what you put in to start with. But the important thing is that as soon as the hydrogen iodide is formed, it actually starts to break down again. So, it immediately starts to go back the other way. All right, so as soon as that forms, what's the word I want here? Let's just say it breaks down again. So, in other words, literally just reverse that equation and you get that. All right, it's fairly self-explanatory, nothing too complicated there. But, where does this stop? Or where does it seem that it's reached an equilibrium? Well, that word is the important thing. The equilibrium point is somewhere between those two. So you get a mixture in your vessel that you've contained these gases in. You'll get a mixture of hydrogen and iodine and hydrogen iodide. It won't just all turn into one or turn back into the original. So this is what we're looking for. We're trying to find the point at which essentially the rates of the reactions are equal in both directions. And if we can predict that, then we can actually interfere with the concentration of reactants and temperature and pressures and all this sort of thing to actually drive the reaction more in one direction than another. All right. Now, a lot of reactions you would think of as only being one direction. You can't imagine them going back the other way. For example, if you've got iron reacting with oxygen in the air to form rust, you can't imagine that going into reverse, and that's because the equilibrium point is so much closer to the rust end, the iron oxide end of that reaction, than it is to the iron and the oxygen. You can't get it back to go back the other way. And this will lead us sort of quite nicely into the last learning outcome, the redox, and about why reactions happen anyway, whether a reaction is actually feasible. You can put two chemicals together and they don't react. Why? Or you put two others together and they do react. Why? And that's what the last section will actually be about. So, without getting too sidetracked on this, this word then, equilibrium, so at our equilibrium, this is where we're going to have the rates of both reactions are equal. Okay, so it doesn't matter which way you write this. So you could write it that way round. Or, of course, you could write it the other way around, which I'm not going to do. But when you consider this, we talk about the forward reaction and the back reaction, or not so much reverse, but the forward reaction and the back reaction. So you can actually change the direction depending on the conditions, and this is a lot of what we've got to look at, obviously. So okay, so it can be made to go either way. Well, theoretically it can, right? In reality, there will be, well nigh impossible reverse reactions. Right, but there's a principle behind all this. It's called Le Chatelier's principle that we're working up to. And Le Chatelier's principle, I'm not going to go into it now, but basically says if you disturb an equilibrium in some way, then the equilibrium will change. The equilibrium point will change to rebalance it. So, you can actually change quantities, if you like, temperatures, pressures, that sort of thing. And, you can change where the equilibrium is actually set up. If we, as an example of this, if we were to have a piece of glass tube, and in that glass tube we put some iron filings, let's say. All right, so iron in here, and we heat it. All right, I've got a bit further to go with this. And we pass steam over it, which of course would be water in a gaseous state, not liquid as we would normally write. Then we get a reaction where, well, what's going on here is the iron, solid, and water. In this case, so just checking my notes, I have put gas. The reaction that we will actually get, and I'm going to do the one-way arrow for a reason here, we get an iron oxide that you've met before, which is the Fe3O4, and that's the iron 2,3 one that it wanted a drawing on here somewhere, didn't it? I think it might be, that's the one. It's that one. So iron, iron 2,3. So they actually call that tri-iron tetroxide. It's a bit of an odd one, that one, but that's one way of forming it. That is formed as a solid there. And what do you think we're left with out of that? What might we find as a gas produced? Hydrogen? Yeah. All right. Now, the way this works is that if we're passing steam through here, the iron, becomes the iron oxide, but the steam keeps passing through. So what's going to happen to the hydrogen? It's actually going to get swept away. Now, theoretically, this is an equilibrium, but if you remove the hydrogen, would it be able to react with the iron oxide to go back the other way? Well, no, it's not, is it? It's just not there. It's being taken away. So you will actually push the equilibrium. If we were to write this as an equilibrium, we'd be pushing it towards the right-hand side because the hydrogen's being removed. And so it's got no choice but to go that way, if you like, or because you're actually upsetting the equilibrium, it will keep going left to right to try and rebalance it and to put more hydrogen in. And that makes it sound like the chemical reaction's actually got a choice in this. But, you have to be a little bit careful, not to use or not to anthropomorphize. So what we have happening here then, the hydrogen is swept away by the steam. So yeah, I'm not going to say that it can't reverse at the moment. That's just a point to make here. But if you had different conditions, and you probably now work out what they would be, all right, so we can adjust the conditions obviously to make this work. Products, well, the products won't be products anymore, but the products would react and the steam would be swept away. So, you know, you can imagine a different physical arrangement where you would be starting with triion tetroxide, you would put hydrogen over that, you'd feed hydrogen gas over that, and you'd be getting iron produced as a result and water, you know, steam coming out the other side. It's not easy necessarily to do these reverse conditions, but if you, you know, if you take away one of the products, then you can actually keep a reaction going in that particular direction. So, you know, what you would have there, just literally reverse it, don't really even need to write it, but it just sort of completes the picture, I suppose, and I've not left myself enough space, have I? I didn't balance that. How did you let me get away with not balancing it? Right, how many iron? How many water? How many iron tetra? That's all right as it is, isn't it? How many hydrogen? Yep, well done. So yeah, if we go back the other way, and I've really not left myself enough space for this one, got to write very small. So you can get it to go the other way, and you get your 3 iron and your 4 water. Okay, so far it's not rocket science. So essentially the reaction is reversible, but usually you know, you would define normal conditions and they will tend to be one way under those conditions, but it's having this ability to manipulate reactions. So tidy off that bit with that. So right, these particular reactions are reversible, but one way. Normal is it's a tricky word to use in chemistry, I suppose. You know, you'd be saying standard temperatures, pressures, states, and all that sort of thing. All right, let's do one more bit on this, and then I'm going to attempt a demonstration which I messed up last year, and then introduce this idea of Le Chatelier's principle. It's very straightforward. It doesn't really explain anything. It just sort of tells you what happens. And that then is a sort of clean place to finish on the theory side of it without having got to too far into anything that requires calculations that might interfere with the calculations you're doing on rates, because yeah, we don't want to mess those up. There's plenty to do on that. Okay, what we have then, this idea of reactions moving about all the time, you know, perhaps going more one way, then going back the other way, and trying to find that point where the rates are going in equal the rates are equal in both directions. How we describe this then, the idea is that they are dynamic, they're moving. So dynamic equilibria, and we want to, refer to reaction rates really, because that's, because we're doing it in this section, the idea of reaction rates hopefully will help us see what's going on. If we've got a simple sort of reaction where A and B react together and give us product C and D, but equally C and D could react together and create A and B. A plus B gives C plus D as our forward reaction. C plus D gives A plus B as our back reaction. If we start with A and B, because we're assuming that those are our reactants, if we start with those at the highest concentration, well, the rate's going to be high. We know, you've just done this, generally speaking, if you increase the concentration, you'll increase the rate. We know that doesn't always apply, but, we're making some assumptions in terms of the type of reaction. But, of course, as the reaction goes on, the concentration of the reactants falls. And that's one of the things that you can't actually take account of, isn't it? You think of the assignment that you're writing up. You've looked at the effect of concentration on the rate of reaction. So you've had, let's say, you changed your thiosulfate concentration from 0.1 to 0.08. Well, all right, you started off at 0.08 and you do the reaction. Well, as the reaction takes place, of course, the thiosulfate is used up. So the rate actually slows, doesn't it? So it's very hard to actually sort of allow for that, because yeah, I don't know that the maths is even possible. It must be somewhere, I'm sure. But we start with the highest rate. The rate of a reaction will fall as the reactants are used up. So if we start with A and B at their highest concentrations, and we're going to find that when we get onto the calculations with this, that we're always we're given values for the starting concentrations of the reactants, and then we're told how much of something there is, how much of one of the products there is at equilibrium, and you then have to work out all the different concentrations at equilibrium. And people make the same mistake every year on this. So I know what it is. So hopefully we'll start with some idea of what's likely to go wrong. So if we start with the highest concentrations, all right, the rate's going to be highest. And then as they react, their concentrations will fall, so the rate falls. So if you're going to plot that on a graph where you'd got rate against time, oh, that sounds familiar, doesn't it? It is like, you've done, by changing the concentrations, you've made the rate fall anyway, haven't you? But if you just started with one concentration and left it over time, then your rate of reaction, time is a sort of relative thing, because obviously some reactions take place in fractions of a second, others might take years. So, the rate is just going to do that. All right, so that's the rate of the A plus B reaction. Okay, so over time the actual rate's going to come down because the reactants are being used up. Theoretically, you could just use them all up. They've all gone. That's that. It's not necessarily going to be the case. Now, at the beginning, you haven't got any C and D. This is the way we're working this one. We're just saying, right, let's bring A and B together. They react. Oh, there's less and less and less of them. But we're starting to get more C and D produced. So the quantity of C and D will rise. So the rate of their production, or the rate of that reaction, actually the rate of the reverse reaction, can increase. But let's come back to that. So we've got no C and D at the beginning. All right, so the rate will be its lowest at that point. In fact, there won't be any. There won't be a reaction. All right, so the rate, I should have put the rate of C plus D reaction. That'll make sense when I draw the little graph for that. But they're going to start forming, so as they form, and their concentrations rise, the rate of the reverse reaction can rise. So as they form, their concentrations and rate of C plus D reaction, so that and that, they both rise. So you've got, for this one then, what are we measuring? Rate against time. Sorry, lost it for a minute. Okay, so we get that effect. So we're getting more and more C and D, so that right to left reaction, rather than calling them forward and back reactions, I have a bit of a tendency to call them left to right and right to left. Now this is fine as long as you don't have a problem with left and right like I do. So beware, if you if you think I'm saying the wrong one, I probably am. All right, forward is the left to right, and the back reaction is the right to left, as they're written on the board. So yes, if I say forward and I'm going the other way or whatever, then yeah, watch out. So this is the rate of the C plus D reaction. So this is why we're going to get the reversible reaction. We're going to get one rate falling from its highest, while the other rate rises from its lowest. And so we have to reach a point, don't we, where the rates are equal, and the formation of C and D is matched by the formation of A and B. So let's see if we can draw that. So eventually, this isn't too scary at the moment, I hope it is. So eventually the rates equalise, and where that occurs is of course what we're looking at. So A and B converted to C and D at same rate that C and D converted. I'm saying the same thing over and over again really here. It's not it's not something magical and new with each sentence I write. It's just to make sure that we're getting a solid starting point here. So what you end up with then, I suppose that would work better if I'd used colour, wouldn't it? Too late. If we've got our A plus B1 coming down and our C plus D1 coming up, all right, so that's A plus B. That's C plus D. Eventually, of course, yay, there is equilibrium. That's what we're trying to To that point that's coming down, to that point it's coming up, and then it seems as though nothing is happening. But of course they are. They're both just happening at the same rate. All right, so it's quite important to understand that this has to happen in a closed system. Now, the idea of a closed system, you might vaguely remember, and I'd be surprised to be honest, at the end of the first learning outcome I did that little diversion on thermodynamics and talked about systems, where you've got an open system that can exchange materials and energy with the environment. You've got a closed system which can, I can't remember which, exchange energy but not materials, and then I can't remember what the other one was. Was it isolated, where you can't exchange anything? I can't. Yeah, I think the only. I can't remember what we were looking at that point. It was all the entropy thing, wasn't it? Which I will have to come back to at some point. But this idea of a dynamic equilibrium, you've got this reversible reaction in a closed system. You can exchange energy, so there will be heat changes going on, but you can't add anything to the system or take it away, all right? Because if you do, then you end up back where we were with that, the iron and the steam, yeah, where the hydrogen was being taken away. You don't reach equilibrium there because you're removing one of the products. You haven't got it there to be turned back. So at equilibrium then, the quantities of everything in the mixture remain constant, not equal, but constant. The reactions are continuing because the two rates are equal in both directions. And then, you know, if you decide to change the conditions of that reaction in some way, then you change the position of equilibrium. So you'll change the amount or proportions of substances in the equilibrium mixture. And that's sort of where we're heading with this. Right, let's pause that. This bit then on Le Chatelier's principle, we always used to just refer to it as LCP when I was doing my A-levels. It's not an explanation, right? It's just, as it says here at the top, it's no more than a useful guide to help you work out what happens when you change the conditions in a reaction in dynamic equilibrium. It doesn't explain anything. All right, so that's, you know, it's just useful to say to yourself, right, if we've added more of this, then the equilibrium will change to remove that, because that's Le Chatelier's principle, is that equilibrium will be restored. And so where you've got a statement of the principle down there, if a dynamic equilibrium is disturbed by changing the conditions, the position of equilibrium moves to counteract the change. I would write that down, but you've got it there in front of you. But that is, you know, that is the key. So I'll just see printed notes on that. Okay, so I'm not probably going to add very much to this at all. And if you then apply it to different changes of conditions, we've got on here using it with a change of concentration, and then you've got with a change of pressure, which of course only applies to gases. Then you've got change of temperature, and right at the end, catalysts. So we're just briefly going to go through this and look at, you know, what we should be able to predict using this principle to actually think about restoring equilibrium. First of all then, change of concentration. All right, if we change the concentration, then we are changing the amount of either one of the reactants or one of the products. All right, it's unlikely to be one of the products, except that, you know, think of that example we had earlier on with the steam going over the iron. then because the hydrogen was being removed, that is removing one of the products, so it's changing the concentration of the products, and that will shift the equilibrium towards the production of more product. If you take product away, then the equilibrium will try and make more product, so it shifts it from left to right on that one. It's in favour of that forward reaction. So the example that you've got here, an equilibrium between four substances, A, B, C and D. And yes, that hasn't printed very well, has it? It should say A plus 2B gives, is in equilibrium with C plus D. All right, so that's, we'll need to sort of add bits on the board to go with this, because you need to go over some of those letters, because what it looks like is A plus 2D gives C plus C, almost. So the example given here then, what would happen if you change the conditions by increasing the concentration of A? Well, the equilibrium, all right, set up like that, doesn't want more A. So the equilibrium will change in order to reduce the amount of A if you increase it, and so that will push the equilibrium in which direction? To the right? Yeah? And that, you can use that, and it's a very simple idea if you think of industrial processes where, let's say A is very cheap, B is extremely expensive, and what we're trying to make is C. And you want to use up all your B because it's really expensive. You don't have to buy lots and lots and lots of both of the reactants. If you just add more A, which is really cheap, B gets used up. So it's, it's a really sort of straightforward application of it. So if we increase the concentration of A, the position of equilibrium moves to counteract the change. All right, so we're increasing the concentration of A. I'm going to put LCP. Write that every year, and it reminds me of my A levels. It doesn't explain it, all right, but it states that equilibrium equilibrium will, the position of equilibrium will move to counteract that. And the only way you can do that is to reduce the amount of A, and the only way you can remove the A is to increase the left to right reaction, the forward reaction. So to remove the extra A, or to remove A, equilibrium moves to the right. Or it sort of favours the forward reaction, if you like. It's used exactly the same example as I just gave over the page. It's a useful way of converting the maximum possible amount of B into C and D. You might use it, for example, if B was relatively expensive, whereas A was cheap and plentiful. You see, I've got Jim Clark living in my head now. This is the problem. So I've used these things so many times, it's almost like, sort of predict what's coming. Ooh, just said that. And I haven't read ahead. You can tell I haven't read ahead today. I'm relying so much on this. Obviously, you've got the other option is if you removed some A. So if you decrease the concentration of A, again, if you use that principle, equilibrium is at a point where you've got a certain amount of A, certain amount of B, certain amount of C, certain amount of D. So if you take some A away, the equilibrium point will move to try and restore the amount of A that you had. So, this is just the sort of reverse, really. So, if you reduce the concentration of A, very abbreviated, Okay, same sort of approach. So in order to make more A, because this is an equilibrium, this is not just reactants and products. You could think of left-hand reactants and right-hand reactants. And none of them are products, but you know they obviously are. You have left and right-hand products as well, depending on which reaction you're looking at. So it, you know, it's not that the reaction is trying to make C and D. It is going both ways. It's actually trying to make both. It's trying to reach a point where both are being made at the same rate. So if you reduce A, then the equilibrium moves to the left to counteract the change again. So an increase concentration of A. All right, so fairly straightforward, and that was the supposed to be the principle behind adding the water, adding the chloride ions. Now the next bit, right, this is about concentration. The next bit is about pressure. Now, the thing about pressure is it's the gas version of concentration, isn't it? Think about it. You know, if you've got a decimeter cubed container and you've got, I don't know, 1 mole of a gas in there, well, you wouldn't have. Well, you could have, but 24 decimeter cubed is a mole. Normally, let's say we've got 24 decimeter cubed, and that's a mole. You try and put more gas in there to increase the concentration, you increase the pressure, don't you? So pressure, like I say, is the gas version of concentration in a solution. The thing that you also have to remember, though, is the number of molecules or number of moles in gases. So there's a slightly different situation here. Changing pressure in gases. You have to remember that 1 mole of gas occupies 24 decimeter cubed at standard temperature and pressure or room, oh, I can't remember. I'm going to put STP, standard temperature and pressure. So if you take a reaction where the number of moles is different on each side of the equation, which it perfectly well can be, you know, you could have 1 mole on one side, no, 1 mole reacting with 1 mole on one side to produce 1 mole of something else on the other side. All right, so if, for example, you have A plus B, this is me just sort of thinking, and it may make no sense at all. All right, if we've got no balancing to do there, if this is 1 mole, then 24 decimeter cubed plus 24 decimeter cubed is going to create, no, that's 1 mole. It's 24 decimeter cubed. So what's happened to the pressure? Well, if you've got, it reduces, doesn't it? Yeah, you've got essentially 2 moles on that side and 1 mole on that side. Yeah, crammed into the same space, as it were. It's yeah. No, I'm just sort of wondering if if you're on my wavelength or whether I'm existing somewhere else today. I think it's it's not looking promising. If we had that, then the pressure would stay the same.
Yeah. Oh, okay. So.
All right. That the pressure would stay the same.
Yeah.
Yeah.
You have
Yeah, and what you've got to think is, if you just took it at its smallest possible level, one molecule plus one molecule producing two molecules. So you've got two molecules on the left, two molecules on the right. In terms of gases, they occupy the same space. All right, now if we, however, do it with just one of those, then 1 mole on the left plus 1 mole on the left produces 1 mole on the right. You're only actually producing half as many moles. So if you had them in a container, you've only actually got half as many particles on the right hand side, so the pressure would drop, wouldn't it? By half. Yeah, it would only exert half as much pressure because you've got two. Think of it in a container over here and over here. Here we've got A and B. Here we've got C. Which one's at the higher pressure? A and B. Yeah, because you've got twice as many particles colliding with the walls of the container. So that produces twice the pressure that does. So this is what you have to consider when you're looking at changing the pressure. All right. So let's take Uncle Jim's approach, because I think I'm confusing matters a bit. So I will remove that. And I know that we're sort of on the downhill slope a bit now, aren't we? Right, let's just work through what we've got here. So again, you know, according to Le Chatelier, position of equilibrium moves to counteract change. So if you're going to increase pressure on a container, then the direction would change to reduce that pressure if that is possible. And it's according to the number of particles. If you've got the same number of particles on each side of your equation, you can't. So pressure is caused by gas molecules hitting the sides of the container. We know that. The more you've got, the higher the pressure. So your system can reduce pressure by producing fewer molecules. So let us use this one. Does it start on the previous? No. Have I lost a page? I haven't got an example. Which one are we using? Oh, it's still the A plus 2B. All right, okay. If we're still using this one. Okay. If we increase the pressure, what does Le Chatelier say we want to do? Decrease the pressure. Which side would result in fewer particles? The right-hand side, yeah? So it will actually push the reaction in that direction. So increased pressure, the result of that is, I'm trying to think of the best way to write this. Equilibrium moves to the right because right side has fewer particles and that will reduce pressure. So you can fairly obviously, I hope, work out what will happen if we reduce the pressure in the chamber or container or whatever it is. It will try and increase it and push it to the... You increase pressure by pushing it to the left. Yeah? So, you know, once you've got the idea, you have to think in your head that gases are a bit different, that you do have... you know, the space occupied by 1 mole of gas is constant, that 24 decimeter cubed. So, you know, if you've got different numbers of particles on the two sides of the reaction, then it's going to have an impact on the pressure. Right, so yeah, that's how it continues down that page. So if we increase the pressure, it shifts it to the right with the fewer molecules. If you decrease the pressure, it will shift to the left because there are more particles on that side, so it will increase the pressure. So fairly, it's there in the notes, so you don't need to write it. So shift to left. Okay. Right, we'll whiz through the rest of this. Yeah, what happens if there's the same number of molecules on both sides? Nothing. Because you can't, there is no change in equilibrium that will help. So if you've got A plus B gives C plus D, we haven't got a 2 there, then you can increase the pressure, but it won't affect equilibrium. You could decrease the pressure, it won't affect equilibrium, because you can't produce more particles or fewer particles in order to change the pressure. So if there's the same number on each side, and that's quite important because you can sometimes ignore, for example, the volume of a container in a calculation, because if you've got the same number of moles or molecules or particles on both sides of the reaction, that's irrelevant. All right, because you can't make any changes to it. The next bit then, temperature. If we change temperature, yeah, we're nearly there. If we change temperature, it will depend on whether it's an endothermic or exothermic reaction. So that's what I was trying to do earlier. So changing temperature. It's not really correct to think of them as reactants and products, but it makes it a little bit easier because it then fits in with the same idea as changing concentrations, doesn't it? If you change the amount of heat on one side or the other. So you need to know endothermic, remember. Endothermic is where you get the cooling effect on the environment, so delta H is positive, all right, the reactants gain heat energy. It's equivalent to heat as a reactant. I should use 3 lines for equivalent to, not equal to. All right, I don't know if anyone, have you come across the 3 lines before? 3 lines means this is equivalent to. An exothermic reaction, where your delta H is negative, is equivalent to having heat as a product. Now, of course, for any given reaction, one of the directions will be endothermic, the other will be exothermic, won't it? Because that's what you were doing with Hess's law, reversing, flipping the values. They're getting it, getting positives and negatives reversed because you were going the other direction. Yeah, this does all link together. These are not isolated topics. So, for any situation where one is positive, then the other one will be negative. And I think it's time we finished as quickly as we can. All right. So you're always going to get that, and they will be equal sums. So depending on what you're given a value for, you can make an assumption for the reaction in the other direction as being the same number but with the other sign. Okay? So you've got some examples about this. So it's still using A plus 2B giving C plus D, this time with a delta H of minus 250 kilojoules per mole, so it's exothermic. That means heat is essentially on the same side as C and D. Heat's evolved. If you were to do it the other way, of course, C and D going to A plus B, sorry, the A plus 2B, then it would be the 250, but it'd be positive in the other direction. Okay. Now, if you change the temperature, then, if you increase the temperature, For an endothermic reaction, that's quite useful, isn't it? It's increasing one of the reactants. So it will push an endothermic reaction in that direction. You're adding more heat to it. But if you've got an exothermic reaction and you warm it up, that's not going to help. It's not going to keep that reaction going. It's actually going to try and push it back the other way because it's already making heat. So it's going to try and get rid of the excess heat and go back the other way. All right. So for if your delta H is positive, your endothermic one, increasing the temperature. All right. So if you have an endothermic one and you increase the temperature, equilibrium, I'm going to say moves towards the product, so we can have it going either way. Products of that reaction. And of course, if you reduce the temperature for an endothermic reaction, well, that's going to slow it down. So equilibrium would move towards the reactants. I will recap this when we come back because chances of remembering it are slim, and I'm just talking about me. All right, so if we've got an exothermic reaction producing heat, then if you increase the temperature, Le Chatelier's principle says, you know, you've added extra product. So it tries to get rid of that product by pushing the equilibrium back towards the reactants. And then, not surprisingly, if we cool an exothermic reaction, we're taking away one of the products, aren't we? So it'll pull it in that direction. So reducing the temperature, equilibrium moves towards the products. So, you know, if you've got a reaction that produces a lot of heat, then you introduce a cooling system to remove that heat. You will keep the reaction going because you're taking the heat away. And Le Chatelier's principle says, you know, the equilibrium will move to counteract that cooling effect. Right, we can't have a lot left to do, and it really is just that last little bit, which catalyst just doesn't make any difference. There we go. Catalysts speed up the reactions in both directions, so yeah, it doesn't doesn't actually change the position of equilibrium. Gives you why use a catalyst. A catalyst just speeds up the rate at which you reach equilibrium. That's all. So yeah. So, whoops, just get there quicker. I was going to write. Okay. Whew. Yeah, I think I've had enough. Yeah. Bye.